Hello. Today we will be continuing with the last topic that we discussed here, which is nothing but the shear force as well as the bending moment diagram. So hope you all are very familiar with the sign conventions, the procedure that we have to follow to solve the shear force and bending moment diagram, and the shortcuts or the curve that we have to use when we draw the distribution. So directly we will be going into some solution of some questions. Let us see. Let's go to the question. So we have already explained the shear forces, the sign convention in the previous lecture. So kindly, if you have not followed that, kindly go back and see that particular video about the shear force and bending moment diagram and the sign convention used for the bending. And we have derived the relationship between the shear force, bending moment and load. And finally we learned how to connect two different points when we draw the shear force and the bending moment diagram. So these are the steps that I have explained to draw the shear force as well as bending moment diagram. Now let us solve a question. See, this is a very conventional type of question which we can find. This is an elementary level of question. So first we have to learn how to solve this question. Then we will go to some complex type of questions. So in this question we have a simply supported beam with only point loads in it. We have a load of 20 kilonewton and 40 kilonewton acting at a distance of 3 meters and 6 meters from the support A, and we are supposed to draw the shear force diagram as well as the bending moment. So I will explain step by step, and you also try to follow this step when you get a problem. So this is the actual question we have, and we are supposed to draw the free body diagram of this question. This is the free body diagram. So we have two reactions at A, which is the vertical reaction as well as the horizontal reaction, and we have one reaction at B. So our immediate aim should be the calculation of the reactions RA and RB. And I have calculated the reaction RA and RB here, which is nothing but 30. So for this particular question, I will show you how we can calculate the reaction RA and RB. This is actually RAY and RBY. So that's very simple. It is like this. See, first of all, we are going to take summation of Fx is equal to 0, which is going to give you the value of Rax equal to 0. Right? So this value is equal to 0. Now we will go for the Fy equal to 0, which is going to give you Ray plus Rby minus 20 minus 40 equal to 0, and we can say that Ray plus Rby equal to 60 kilonewton. And after that we are going to take the moment equation. We will use the moment equation like net moment equal to 0, not moment at the point A equal to 0. We can take the moment at B equal to 0, doesn't matter. So the value is going to be 20 into 3 plus 40 into 6 minus Rby into 10 equal to 0. So Rby equal to 60 plus 240 divided by 10, the value is nothing but 30 kilo. So if you substitute it over here, it will give the value of Ray as 30 kilo. So this methodology is the first step you should adopt when you start the solution of SFD as well as BMD. You are supposed to find out the reactions. Now this is the methodology that we have. We are supposed to use Fx is equal to 0, Fy is equal to 0, moment equal to 0. And don't conclude that always the reaction will be same. No, for this particular question, we got both the reactions as 30. It can be two distinct values. It can be one can be a positive value, the other can be a negative one. So that doesn't matter. Thing is that you have to follow this procedure, and whatever might be the value you get as the reaction, you have to use for the construction of SFD as well as BMD. Now let us use this particular values for the solution. Right now we are going to solve the SFD as well as BMD. Okay, so I will write the value of RAX is 0 and AY is equal to 30 and RBY is also equal to 30. So this is the reaction side. Now I will do one thing. I can draw it over here on this side. Downward I can draw, or this side. Both will be okay. So for the time being, I will construct the SFD BMD on the right hand side, left hand side, and the correct calculations will be on the right hand side. Okay. So always make sure that it is you draw the SFD and BMD right below the actual loading diagram, or it can be under the as a freehold diagram or the actual loading diagram. So make sure that you draw your SFD as well as BMD right beneath the loading diagram. Okay, so that is always better to understand or to get a physical sense of the problem. So right now I'm going to do. So I will be drawing the SFD and BMD right beneath the figure which is on the left hand side of the screen, and right hand side will be used for the calculation purpose. So first step we have completed. We have calculated the reactions and the value obtained is 30. Now we are going to calculate the shear force diagram. So before moving to the calculation of shear force diagram, I want to add one thing here. See, when we calculated the reactions RA and RB, see what was the sign convention that we used? See, we used the conventional type of sign convention. We haven't used anything related to the shear force or the bending moment diagram. So whatever sign convention you learned in your subject of mechanics, you can apply for the calculation of RA and RB. That means you can consider the clockwise moment as positive, counterclockwise as negative. That is your wish. So you can use that kind of methodology or sign convention just for the calculation of RA and RB. And don't try to use that, or please don't mix that sign convention with the one that we use for the shear force and the bending moment. Okay. So keeping that in mind, I'm going to start the process. So first of all, let us start with the shear force diagram. So it is better to write it as shear force, not the shear force diagram. Now the question is how to start with. I will be starting from the right hand side to the left hand side. This is what I'm going to do. From the right hand side, I'm going to travel towards the left hand side, and I consider a section which is traveling right ahead of me. This section is going to travel. So if I take the point B, the section will be right ahead of B, just ahead of. It is not too far away, it's very close. Okay, so this section plane is very much needed for giving the sign convention for the sign for the corresponding nodes. So this is a section. So this section is going to travel from point to point. And now I will name the point, this is C and D. I will change the name as, I will shift the name. I will give this as D and this as C. You can use any name. Just for the simplicity, I just noted it as C and D. Okay. So just see where all we have to take the shear force. That's the next question. So I told that we discussed that you have to take the shear force at all the location where you can see an abrupt change in the load. That means if you start to travel from B, we have a section plane right ahead of us, which is XX. So if I look towards the right hand side, then we can say that the shear force at B is equal to minus 30 kilonewton, because this minus 30 is acting on the right hand side in the upward direction, which is considered as negative. Okay, so we have given the sign negative. So if I started to travel from B towards C, your section plane C is also moving along with you. Just before reaching the C, if you look towards your right hand side, you will have the same value 30 kilonewton in the section CB. between the section C and D. Between, I'm not talking about at the point C. At the point C, something is going to change. So, till we reach the point C, we have a shear force of 30 kilonewton negative on our right hand side. There is no change in that. And what is a shear force at C? See, when you reach the point C, your section plane is right ahead of you. It's very much in front of you. It's very close. So if you consider the section plane and if you give the corresponding sign convention, 30 is going to take the negative sign because it is acting in the upward direction, but 40 is acting in the downward direction in the right hand side, which is considered as positive. So this is going to be take a negative sign, this is going to take a positive sign. So the value of C, so the shear force at C is equal to minus 30 plus 40, because 40 is acting in the downward direction when considering the section. So the value is equal to plus 10 kilo. So suddenly it has changed to 10 kilo. Now we will calculate the shear force in the section CD. So if you make this section to move till D, and if you look towards the right hand side, you still have only two loads, 30 and 40. So the value is also remain same as that of 10 kilo. Now we will consider the shear force at D. So if you consider the shear force at D, this 20 kilonewton is also going to contribute. So right now we have a section plane just in front of your 20. So we have a minus 30 here. On the right hand side you have a plus 40. Again you have a plus 20 here. So the total value is going to be how much? 30. Okay. So 30. So that 30 is available here. So when you reach the point reaction at A, the value has to be 30 because we have a 30 here. So that is another way to understand what is the value of shear force at A. At B it is 30 minus 30. At A it is going to be plus 30. So we have obtained the value as plus 30. Right. Now it's our time. It's time for to plot the SFD and the. So I will draw some vertical lines to make the things very easy. Okay. So I will draw a reference line. I will draw a reference line here. Just for the understanding purpose. Now let us start the shear force diagram. So what was the value of B? Shear force at B was minus 30. So roughly there is no scale. There is no need to choose any scale. You have to just mention the value. So this value is going to be minus 30. So up to the point C, because this was your point C and this was your point D. So up to C the value remains same, right? It is minus 30. So when you join 2 point loads, it has to be by horizontal straight line. That also we have explained in the theory part. So at the point C, what happens? The value jump to 10 kilonewtons, right? So from minus 30, it has suddenly jumped to 10 kilonewton, and it remained constant in the section CD. So the same 10 kilonewton is available till we reach the point D. So upon reaching the point D, the value jumped to 30 kilonewton. So again it jumped to 30 kilonewton, and that remained constant till the point A. So how will we join these 2 points? By a horizontal straight line, because these two are point loads. We have 2 point loads and they are connected by a horizontal straight line. We have a step-like variation here. We have a step-like variation at the location of point load. So we have a step-like variation here, and again 2 point loads are connected by a horizontal straight line. At the location of the point load, we have a step variation, and finally we do this. So this is the shear force diagram. So I will use some other color for making it more. So this is the shear force that we have. That you cannot a sudden jump in the. So this is negative. This is positive. So if we can shade it for a better understanding. So this is how the shear force diagram is going to look like. So whatever we have discussed in the previous session is clearly applied here. Okay. So I told that whenever there is a point load, you can have a step-like variation in the shear force diagram. So if you look here, there is a step-like variation here. So at the locations of point loads, we have step-like variation. So how can we obtain this step-like variation? The simplest method is to take two shear forces at that particular location of point load by considering the point load and without considering the point load. So if you look at the point C, I have minus 30 here. I haven't selected the 40 kilonewton normal. That means without considering this point load at C, I have a moment of I have a shear force of minus 30. When I consider the point load, the value changes to 2. So in order to get a step-like variation, it's very simple. You calculate two shear force values at that particular location where the point load acts. One by without considering the point load, and after that considering the point load. So you can easily get a shear force diagram. So we have completed the shear force diagram part. Now we will go with the bending moment. So I'm going to calculate the bending moment. So we have selected the bending moment. We have selected the shear force at B, C, and D. So here also we will go with the bending moment at the locations B, C, D, and A. And we know that the moment at B is 0 because at the supports, definitely the moment is 0. And again we are started to travel from B to C. And if you take the moment at C, we have moment only due to the load 30 kilonewton. Because 40 kilonewton is acting at the point C, which will not create any moment B at C. And we will consider 30. So 30 is creating a sagging effect. If you look here, this 30 is going to create a sagging effect. So the value is 30 into 4. The answer is 120 kilonewton meter. Now I will take the moment at D. So when you take the point D, you have two loads on your right hand side. One is 30, which is acting in the upward direction, and another force 40 kilonewton, which is acting in the downward direction. So again 30 kilonewton is going to create a moment of 30 into the total distance is 7 in the upward direction. That means the net effect is a sagging effect. If you look here, you can see the sagging effect here. This is how the load 30 is going to, this is the effect that the load 30 is going to impart on this particular beam. So we have selected the value 30 into 7 as the value of bending moment. Since it creates a sagging effect on the beam, we consider it as positive. Now we have taken the effect of 30. Now we are not bothered about 30. We are neglecting that force. The next force we have to consider is 40. So what is the effect caused by the 40? 40 creates a hogging effect. If you hold at the point C, and if you apply the 40 kilonewton individually, don't consider 30 here. 30 we have neglected. You consider 40 here. So how the 40 kilonewton, what moment this particular 40 kilonewton is going to give on the beam at the point D? The 40 kilonewton is going to give 40 into 3, because the distance from D to 40 kilonewton is 3. So 40 into 3 is the magnitude of the moment. And what is the sign we have to use? This 40 into 3 moment creates a hogging effect. See, if you consider the force 40 kilonewton alone, it is going to bend the beam like this at the point B. So the value is negative, and the answer is 210 minus 120. The answer is 90. Sorry, 110. Sorry, 90. The answer is 90 kilonewton. So the moment at D is 90 kilonewton. And finally, moment at the point A is equal to 0, because that's what we have done when we calculated the reaction. So right now we have the value of moment at B, and let us draw the shear force diagram. So sorry, the bending moment diagram. For that, I will use a horizontal line here. All the values are positive. This is positive, and everything is positive. So the moment at B is 0. The moment at A is also 0. The moment at C is 120 kilonewton. So the value is 120 kilonewton meter. And the moment at D is 90 kilonewton meter. 90 kilonewton. There is no need to take any scale, but a basic scale should be there. There is no need to use any kind of scale or ratios like that, but a vague way of representing it should be there. Some kind of proportionality should be adopted, that's all. So how will we join these 2 points? We know that in order to join these, the bending moment between 2 point loads, we have to use inclined straight line. So here also inclined straight line, here also inclined straight line. The value is positive at every location. So the bending moment is positive, and if you are interested, you can shade this. Just to make this bending moment diagram to distinguish from other diagrams, I am shading it. There is no need to shade also. You just keep it as it is. So this is how the bending moment diagram is going to look like. So if you look at this actual figure, actual loading system, and if you compare your shear force, you can say that, see, we can have a maximum shear at the locations between B and C, which is nothing but minus 30. And between the section B and C, the load is only 10 kilonewton. And between the section A and B, you have again 30 kilonewton in magnitude. So right now we understood the variation of load acting at different locations of the D. And if you look at the bending moment diagram, this is going to be the bending moment diagram, and this is going to be shear force diagram. So when you look at the bending moment diagram, again, the value of bending moment is going to change from point to point. So the maximum bending is available at the section C. It is nothing but 120 kilonewton. So when you design a beam, you should design for the maximum bending moment. So you should design the beam to withstand this maximum bending moment, and that is the significance of the bending moment diagram. So if you want to design a beam, first question is, what should be the bending moment that the beam is supposed to carry? So if you look at the bending moment diagram, you can have n number of bending moments, but which one we have to choose? We have to choose the maximum value of the bending moment. So we chose 120 kilonewton for the design of bending beam. Now this is a very fundamental question which consists only of point loads. Now we will use the same methodology to solve one more question from the with UD, uniformly distributed. So this is a question with UD. Okay, let us solve this question also. So the total length of the beam is 10 meters, and we have a load of 20 kilonewton per meter, and we have 2 reactions. Let us rename this as RAY, and let us rename this as RBY. And we have two another points, C and D here. We have 10 kilonewton. Okay. First of all, we have to calculate the reactions. I'm not going to do that particular step because that's same as that what we have done in the mechanics. So I will name this load as 66 and this as 24. Now we'll start with the problem. So let us write down the shear force at B. So before we jump into the solution part, let us have an analysis of this. And after analyzing it, we will start with the solution. That will help you to understand more about the bending moment diagram and the shear force diagram. See, we have point loads of 24 kilonewtons, and we have a point load of 10 kilonewton here, and we have a point load of 66 kilonewton. So the shear force diagram will have a step-like variation at the location B, D and A. So we can expect to have a step-like variation at the point B, D and A. So in order to get a step-like variation at D, I have to take two shear force values, one without considering the 10 kN and the second one by considering the 10 kN. So let us do that. So the shear force at B is equal to how much? Minus 24 kilo. Why? Because it is acting on the, if I consider section here, right hand side, upward direction negative. Now if I take the shear force across BD, the value is same as minus 24 kilonewton, because till when you reach the point C, there is no other load other than 24. So 24 is the one with the value of the load that is going to act in the section DB. And the shear force acting at C is nothing but, again, minus 24 plus 10. Minus 24 is because it's acting in upward direction when you consider the section here, and 20 is acting in a downward direction, that is going to take the positive side. So the value is minus 14 kilo. Now you look here, when you start to travel from C to A, see there is, when you take a section here, the value, the load is increasing. When you take a section here, again the value of load is increasing. So what are you supposed to get at the location of A? You are supposed to get the value as 66. Now let us see whether we get that value or not. Shear force at A is equal to minus 24 is there, plus 10 is there, plus this 20 into 4. Because 20 is the load acting per meter. So total span is 4 meter. So the value is going to be 20 into 4. So the answer is going to be what? 20 into 4 is equal to how much? 80 plus 10 here minus 24. So totally 90 minus 24, the answer is equal to 66 kilonewton. We have obtained that. Now let us plot this. These are the locations I am interested in. I will drop a horizontal line. I will choose some other color for the shear force diagram. So the value at B was minus 24 kilonewton. So I have marked it as minus 24. Now up to D, the value remains unchanged and it is equal to 24. So when you reach the point I will add one more shear force here. Shear force at D is minus 40 kilonewton. This is by considering the point load 10 kilonewton. I haven't added that. So kindly add that also. So suddenly the value changed to minus 14. So the value changed to minus 14. Now till when you reach the point C, the value remains same as minus 14. So from the point 14, when you travel towards A, the value changed to positive 66. This is a very significant change. So the value changed to positive 66. How will we join this? 2 point loads are interconnected by a horizontal straight line. At the location of point load, we have a step-like variation. Again, we are connecting by a horizontal straight line. From here to here, that means from the minus 14 to 66, between these points, we have a UDL, and UDL is connected by using a inclined straight line, and we got the value of minus. So here the negative, and here it changed to positive. So right now we can see that at a particular location your shear force becomes 0. Here what? This is shear force equal to 0, and this particular point can be called as point of inflection. And based upon the relation, we can say that here we can expect a maximum bending moment. So this is how you have to relate it. You have to club all these things together one by one. So it should work like a well lubricated machine. To do that, you should have all these sign conventions, theory part well and clear in your head. Make it easy for you to draw. Okay, now we are not aware about the location of this particular load. Where is this located? I don't know. So, but we are supposed to find that value. So, how to find that value? I will say that this is a particular section XX where you have the shear force equal to 0. So, I will give the distance as X. I will give the distance as X, and what will I do? The shear force at X is how much? 0. We have to consider all the loads at X. That means this is the location of X. I have to consider this much amount of load, this 10 kilonewton, and I have to consider this 24 kilonewton. All these things we have to calculate. Okay, so let us find the location. How will we do that? So on your right hand side, you have a minus 24, you have a plus 10. So we have taken these two. Now we have to consider the load which is in the shaded part, which is nothing but plus 20 into X. This should be equal to how much? 0. So the value is going to be minus 14 plus 20, X equal to 0, and the value of X is equal to plus 14 by 20. So the value is going to be 0.7. The answer is going to be 0.7. That means this distance is 0.7 meters. Okay, so what will be this distance? This is going to be 4 minus 0.7, 3.3. So this is how you are supposed to calculate the location of location of the point of inflection. Now we are supposed to calculate the bending moment. Let us do that. So the bending moment, let us do. Okay. So what is the value of bending moment at B? That is 0. Same is the case the bending moment at A. Now we have to find out 3 more bending moments, one at D, one at C, and one at the point of inflection. So let us calculate the bending moment at D. That is very easy. 24 into 2. 24 into 2. That is going to give a sagging effect. So positive. The value is 48 kilonewton. Now we will calculate the bending moment at C. The value is equal to what? 24 into 6. Positive, and minus 10 into 4. Because 10 into 4 is going to create a sagging, voguing effect. So 10 into 4. So the value is going to be how much? The value is going to be 104 kilonewton meter. This is the value. Again, we have to calculate the moment at this particular location. Okay, I will say why we have to calculate that. Anyway, definitely we have to calculate that because based upon the theory that we have learned, we know that the maximum value of bending moment is going to occur at this particular point. Now the question is, what if we didn't calculate the value? Let us plot it and see what is going to happen. Let us plot the value and let us see how it is going to be here. So I draw a horizontal line. The value here is 0. Here is 0. These two values are 0. Now I have a value of 48 kilonewton here, which is positive. No problem. Fine. Now we have a bending moment of 104 here. So the value is 104. See, these 2 points are joined by horizontal straight line because we have to connect between 2 point nodes. Here also a horizontal straight line. No issue. So this is a UDL. We know that between the point A and C, the curve should be parabolic. Now the question is, how will you draw a parabola? See, you can draw a parabola like this. This is also called as a parabola. Can be a parabola. This can also be a parabola, but we don't know which is the actual curve. Right? Anyway, we are going to, the nature of the curve is a 2-degree parabola. But the question is, how should we draw it? Where should be the peak? And the answer is this. The peak has to be, so if you look at this curve, the peak is somewhere here. If you look at this curve, the peak is somewhere here. So actual peak has to be somewhere here. That's what we are supposed to do. So we have to calculate the value of bending moment at the location x. So the bending moment at x value is going to be how much? 24 into how much? 2 plus 4, 6, 6.7. Again, minus 10 into 4 plus 0.7, 4.7. Right? Now we have to consider the moment due to this much load. That is equal to negative 20 into 0.7 into 0.7 by 2. So the total distance in this range is 0.7. So the total load is going to be 0.7 into 20. This is going to act in the midway of this particular section, and that is equal to 0.7 by 2. So this is going to be the distance d. This is going to be the load. So load into perpendicular distance. 20 into 0.7 is the total load. It is acting at 0.7 by 2. So we have taken the distance from the sectional plane x, and when you calculate this, you will get the maximum value. I didn't calculate that. Anyway, let us do it like this. So this point is going to be 108.9 kilonewton. So this is how you have to draw the shear force as well as the bending moment diagram. So you try to practice this. Practice makes men perfect. That's the only suggestion and advice that I can give you. You take as much questions, practice as much questions as possible. You select different questions. Apply the simple principles. Don't confuse with the rules and regulations. Okay. So simply understand. Slowly, you will be able to solve the SFD and BMD. So you try out these 2 questions, and then you try to solve some other questions also. So in the next class, I am going to discuss about another 2 questions, which is about an overhanging beam and one more question with a point moment. So for the time being, let us stop here. Stop our discussion here. So kindly go through these 2 questions. So thank you. Meet you in the next video. Bye.